Welcome to another episode of Dominic Does DIY. As always, like, subscribe, and comment down below in order to get that Google algorithm processing if you find this entertaining or useful. Today the boss comes in and has a slight problem. We just got the new boards in and there is something wrong with the layout. The power switch turns the circuit on, but as soon as you release the switch, the unit turns off. As the hardware guy, you have to get this fixed because we need to hand this off to the firmware people. You take a quick look at the schematic and tell your techie to go probe around a little to find out what went wrong with the layout. Clearly something was missed in the schematic because we didn't have any design rule errors on the PCB. So PCB and schematic are the same, but there's obviously a trace missing somewhere. While you are looking at the schematic, the techie comes in and says, yeah, the circuit does not stay on. However, I put a jumper on the board and now the system output stays on after pushing the button. I just can't turn it off with the button press. You notice on the schematic there are actually two issues. Both can be solved with firmware on the next spin. But right now we need to make this work to hand off the board to the FEs. One, there is no way to lock the circuit on. Two, there is no way to turn the circuit off once it turns on. Looking around the lab, all you have are some caps, resistors, 1N4148s, and a tube of D flip-flops. So the question is, where did the techie place the jumper to keep the circuit on? And using the stuff we found, how can we make the switch turn the circuit on and off? Also, what modification do we need to do to the schematic from our circuit to properly be able to send a signal to the micro to allow the micro to turn it off after pressing the button? Pause the video here if you would like to give it a go. So let's go ahead and run the basic circuit real quick and see the output of the system. So we can see here, this upper plot plane, that is our switch. So we can see that the switch goes up, down. So I'm doing two switch pulses here. And we can see that on these switch pulses, right, that the system, it goes high just as expected. Right, so this is what they were seeing. This is what we want because we want to be able to hit the button one time, and then we want the power to remain on. When the button gets hit a second time, we want power to be removed. Right, that's a basic on-off switch. But right now we just got it where so long as the button is pressed, we have power on the output. But if we release the button, we lose power on the output. So what is it that the techie found, or what is the jumper that the techie did in order to allow the system to just remain on 100% of the time, but not turn off? Well, he knows that this is a standard issue switch with the PMOS and the NMOS. So he knew that there was something missing on the gate. We don't have anything on the gate here, just like he was missing. So he just made a jumper between the output of the PMOS here, the main power control switch, the main power PMOS, and he just connected it to the gate. So now when the switch gets pressed the first time, it'll apply power to sys. The system will then supply power to the gate, which will then turn this NFET on, and it'll just lock the PMOS on. So now if we run it again, the output will just be on. And sure enough, when we pull the switch down right here, what happens? The output of the system goes high, and it just remains high, even after the button is pressed again over here. So since this isn't exactly what we want, we know that we don't want to just connect the system to the gate, but we do know that this gate is what turns the output on and off. So we need to be able to control this somehow. Well, what did we have? We had some 4148, some resistors, some caps. And so what do we do with that? Well, if we take a look at this circuit, right, using what we have, we go ahead and build it up, and we're like, well, I want to know I need the system, right? So we'll go ahead and use the system there. I'm going to make something called the power enable bit, and we need to switch, right? So this is using the DQ flip-flop, and we have it set up just in a standard flip-flop action. So we got the not Q output connected to the D input. And so every time we receive a clock pulse, it'll basically toggle the output right there, because when the not Q, let's say that this is 0, it'll put a 0 on a 1, the clock will come in, and well, it'll put a 0 on the D. The clock pulse will come in. Since the D is 0, it'll push that over to Q, and then not Q will be a 1, which will then feed it back into the D. And so we'll just end up with a standard flip-flop right here at every clock pulse. And then how do we create a call? How do we create a clock pulse? Well, we know that a DQ flip-flop, it takes the rising edge. So we need first a high side. And so our high side is going to be our system output. And then we need to be able to pull it low to kind of initiate a clock signal to get pulled back high, and that's where the switch comes in. So what the switch will do is pull the clock line low, and then when the clock line gets pulled low, it will then, on release, when it releases, it'll go back up to your system, and then the clock will see the high pulse, and it'll toggle the output. Now, the output of this is what we want to control the gate with, so that's where the power enable comes in. So if we just take this now and we move that over here, like that, and then let's just bring this a little closer so we can get it all on one screen, right? We'll just do this real quick and move the line up here just to make it a little cleaner. And so now we can see we've got our switch is now going to pull two things low. It's going to pull this point low, and it's going to pull this. It's going to pull this low, which is the gate to get us started. So once it pulls that part low, it'll then activate sys. Sys will then turn on our DQ flip-flop here, which will cause it to toggle. And then the next so we'll have a high on the output. And then because we have a high on the output, that'll engage the power enable here, which will turn the MOSFET on. And then the next time the switch is pressed, then what will happen? Well, we have to actually do one more thing on this. Because right now, what's going to happen is let's run it real quick, and then we'll go over why it fails. Right? So this system right here will fail. And so you can see here, if you look at our output, it's just always on 100% of the time. The reason for that is at boot up, this thing does you see that little spike at the intro right there? And so what happens is it gets basically triggered to be held on. And then once this PMOS is held in an on state because the NMOS is on, then this switch is actually pulled to ground. So, right, because you got 100K there, 4.7K here, this pretty much is ground, right? And so then that means that this is pulled to ground. So in order to prevent this backfeeding into the ground system here on this NMOS and being able to actually use like a toggle system, what we need to do is we need to go ahead and cut that trace right there and put a diode right there. So now current won't be able to flow in this direction through that diode. So now the switch just independently on either one of these will do something on its own, right? So now if I run it, we can see when we press the switch the first time, well, first it starts up and it's able to clean itself up, right? And so when we press the button the first time, then what happens? The system comes on just like we expect. But when we release the button, it's still held high because this is still, it's not got a signal, right? The DQ flip-flop hasn't got a signal yet. But when we receive the next signal, when we release it, which is what we expect, because we got to get the clock signal to go high, right? So when you press the button, you'll pull switch low. And then when you release the switch, right, that's when this clock signal will go high. And when it goes high, the D will flip-flop, and it'll set power enable low, which will then turn that NMOS off, turning off the PMOS. And then naturally this D flip-flop will be powered by system. And so as this system dies, right, this thing will die, and this will always just remain low. So this is how we can get the on-off feature using the DQ flip-flop and the 4148s. So now what do we do for the next revision? Well, we have to first fix up the traces, right? And second, we have to connect in the micro, right? And how do we do the micro correction? Well, this DQ flip-flop right here is pretty much the micro, right? It's doing exactly what the micro is going to do. So it's just instead of the clock signal, this will actually be an input, GPIO input on the micro, and the DQ output, that not Q output that we're using for power enable, that'll just be the output for the micro. So literally the clock is the input and the power enable here is the output. And that's how we would connect it up to a micro. So that's all I have this time. Thanks for watching, and I hope you enjoyed the video. And thanks to all who have subscribed and shared. I will see you next time.